So I'm audible to everyone? Yeah, session will start in another 2 minutes. Hello, good afternoon. Madam, am I audible?
Yes, sir.
Okay.
Am I audible?
Yeah, yes, ma'am. Can you please
Okay.
your slide me?
Okay, 1 minute. Is it visible?
Yes, ma'am. Yes, ma'am.
Yeah.
Yeah. Good afternoon, everyone. It's a pleasure to welcome Dr. Leena Chandrashekar, a distinguished academician, researcher with over 20 years of experience in teaching and research. Dr. Leena Chandrashekar expertise in VLSI, embedded systems, cybersecurity, computer vision, and biomedical image processing. She is a senior IEEE member and has published numerous research papers and holds the patents in biomedical image processing. As an IEEE funded researcher, Dr. Leena Chandrashekar has received the grants for the research and the educational incentives. So she serves as the V2 research supervisor and placement coordinator at RNS Institute of Technology, Bangalore. Dr. Leena Chandrashekar is passionate about mentoring the students and actively supports the undergraduate and the postgraduate research projects. We are honored to have Dr. Leena Chandrashekar with us today. Her contribution to the academia, research, and industry collaboration makes her a highly respected in her field. Please join me in extending a warm welcome to the Dr. Leena Chandrashekar. Over to you, ma'am.
Thank you. Thank you so much, sir. Very kind of you to introduce me to the audience. And I hope I'm audible to everyone.
Yes, ma'am.
So let's start off with our discussion today. And I'll try to make it as interactive as possible because it's being the afternoon session. I think it's going to be pretty challenging to just hear out. So I may ask a few questions in middle just to check if you have any, clarifications. So today's topic is revolutionizing vision, emerging trends in AI-driven image processing. So I would like to pay our tribute to our founder, Dr. RNSIT. And this is going to be the agenda for today. What I will be presenting, I will be talking about my research work, some AI tools which can help us do research. And of course, I would like to share the call for research scholars and project interns from RNSIT and some problem statements in case we have some PhD scholars or some students who are willing to do their research in the area of biomedical image processing or image processing with AI. I have listed a few problem statements. So that's going to be the agenda. I hope you can see the slides moving.
Yes, ma'am.
Yeah, thank you. So my research work was basically focused on detection of glioblastoma, which is a very destructive and a grade 4 glioma. So it is basically a brain tumor which occupies a large portion of the brain and it grows very rapidly. So after detection, it roughly takes about 12 to 15 months to reach its final stage. And the survival rate, as indicated, is 12 to 15 months. And the treatment is pretty long, relatively 2 years, and 2 years survival of only 30% of the detected cases. So this simply means that it's a very fatal brain tumor, which can happen to individuals, and it's mostly sited in the frontal lobe, temporal lobe, or parietal and occipital lobe. So that's about the brain tumor. And now coming to my work, so I worked on image fusion. So basically, I was working on CT and MRI images. So for detection of brain tumors, people usually go for MRI images, whereas MRI images have their own challenges, and they fail to detect the tumors very accurately. Hence, people go for some multimodal techniques, like they go for a combination of CT, MRI images, or PET images, and so on. But again, each of these images come with their own drawbacks. So the challenge always lie with the radiologist or with the surgeons to detect the exact location, or the localization of the tumor gets very challenging. And since it is to deal with the brain cells, extraction of the brain cells can harm the functioning of individuals, and it will take a longer time for the brain cells to recover. And even getting to the brain cells is pretty challenging because the skull is the hardest part of the human body. So there's always a challenge in detecting these tumors. And that's the reason why they have, there are novel techniques to do that in the imaging itself. And after imaging, people combine these multimodal images. So that's where my work lies. So medical image fusion is basically a process of combining complementary images which are coming from different sources, and resulting into a single comprehensive image. So the image fusion can be performed in pixel level, feature level, or decision level. However, the pixel level seems to be more accurate and more precise. So that is the reason why I have focused on the pixel level image fusion. So these are some of the sample images I would like to show to the audience. So the first image, what you see is a CT image, and the second one is a MRI image, and then you have a PET image. And of course, these images come in different resolutions. You have 630 cross 630 image, which is unsigned int format, or you have 512 by 512 image, or you have 1056 cross 1056 image, again coming with a different format. So all these images are multimodal because they're coming from different machines. A CT machine is completely different, and MRI machine is a completely different machine. And these machines generate, images which are of different resolution. So there is no standard resolution as such. So each of them come with different resolutions. So our job is to, bring these images to a finite resolution so that we can have the fusion. And next, I'll share some details about CT images. So CT stands for computed tomography image. And the CT image represents the central mass of the GBM, the tumor, which is in short called as a GBM. And CT images are only successful in identifying the central mass of the GBM with very lightly defined margins, edema, and lesion with fluid attenuation. And sometimes, the GBMs may also appear as brain lesions or infraction with hemorrhage or cerebral abscess in CT images. So it never gets detected as the GBM itself. It gets detected as other brain tumors, which may not be so fatal. And that's the reason why doctors fail to identify the tumors. And then, since they grow very rapidly, it mostly leads into fatalities. We have another CT image, which is called as a contrast enhanced CT image, which can indicate some irregularities, solid enhancement, and ring enhancement around the tumors. But again, this involves injecting a radioactive chemical into the human body so that you can have the contrast enhanced CT images. So again, this is going to be limited in a few cases. Not everybody is comfortable with having these radioactive elements injected into the body. So there is very little contrast enhanced CT imaging technique which is adopted in detection of brain tumors. So next we have the MRI brain images. So you can see the MRI can effortlessly indicate the brain lesions with hemorrhagic parts resembling the malignant glioblastoma, and the different regions of the tumor, like the white matter, necrosis, which is the central part of the tumor, the hemorrhage, these get represented with different modalities of MRI images. That is, MRI T1 can detect these things, whereas MRI T2 indicates hyper intense surrounded by vasogenic edema. So again, here also we have to go for different variants of MRI images. And just like the CT, you have contrast enhanced T1 images, where again a radioactive element is injected in the body before the imaging is performed. And this imaging is successful in identifying the variable enhancement, heterogeneous enhancement, or peripheral and irregular with nodular components that are completely surrounded in the necrosis. So necrosis is basically the central part of the tumor. So you can see the image which is shown here on the slide. The MRI images can just show, some kind of irregularity in the image, whereas they fail to identify the exact region. The outline of the tumor is not very, visible, right? It just shows some kind of irregularity in the brain cells. Whereas the contrast enhanced image, what you see on the second figure, this shows a pretty, there's a finite line around the tumor. So since each of these images come with their own, shortcomings, we use these images so that we can have both of the worlds. And you can see some of the challenges here. Individually, CT and MRI images are also affected by noise, and noise in the image can lead to improper detection of the GBMs. And of course, you have poor contrast images also. So some poor contrast images may, not identify the GBM and conclude that lesion. And the role of denoising and contrast enhancement is very, very important in image fusion framework. So even before we perform image fusion, we have to perform denoising and contrast enhancement. And the failure of a single modality image can lead to delay in detection of GBMs, and that can be fatal. So the importance of early detection of GBM is very, very significant here, so that the further treatments can be planned. Right, so that's the challenge with the detection of GBMs. Yeah, so this was the proposed, block diagram what I did in my PhD work. So we have the CT image and the MRI image where we perform some kind of pre-processing where we are denoising the images, and then we perform image enhancement, and then we do image registration. Image registration is very, very important because each of the images are coming from different machines, and the position of the patients may be different when it's acquired from the machine. So it's very important to register the images so that they are all lying on the same axis, and they are oriented in the same direction. So that's the purpose of image registration. And once we register the images, then we perform image fusion using a variety of multi-scale, multi-resolution transforms, like the discrete wavelet transform or the counterlaid transform, or the non-subsampled counterlaid transform. There are quite a few multi-scale transforms which can be used in fusing the images. And then finally, we perform post-processing. And then, of course, we have some analysis after we have done the fusion. And lastly, segment the tumor from the image and then compare it with the individual imaging techniques. So that was my work, what I did in PhD. So these were some of the objectives I had outlined in my PhD work. So first was to develop an algorithm for denoising the CT and MRI images without the loss of any principal edges in the medical images. So it's very important for us to, denoise the image, but at the same time, ensure the edges are not lost in the images after denoising. And contrast is also a very important parameter when it comes to detection of tumors, because this is what is going to help the radiologists identify, the tumors. The contrast is very important in MRI and CT images. Again, the contrast has to be automatically modified. So I proposed a algorithm, adaptive image enhancement technique, which was based on Clahe, and some genetic algorithms like particle swarm optimization was used to select the Clahe parameters so that we could have automatic contrast enhancement. And then coming to the AI part, while doing the registration, I used a deep learning algorithm like the convolution neural network, which was designed all from the scratch. And the application of this was to register the images coming from different machines, the multimodal images. And then I perform multi-scale, I use some of the multi-scale transforms to fuse the CT and MRI images. And the last objective was the central part of the GBM, to detect the central part of the GBM, that is the necrosis, which is like a eye of the tumor. So it's very important for us to detect the central part. So based on that, the localization can be performed. And of course, I compared it with the individual images. So these were some of the objectives I had outlined for my PhD work. And following the objectives, we have the methodology, which is also in line with the objectives. So if there are any questions, I can take it up before we move to the next slide. Are there any questions? Okay. So if there are no questions, I will proceed to the next slide. So coming to the data sets was the biggest challenge in my research work, simply because, getting CT and MRI images from the same patient is always challenging. Most of the times people go only for CT image or MRI images alone. They don't prefer getting both the imaging techniques done, right? So that was the biggest challenge I had with the data sets. And that is when I found the solution with radiopedia.org, which is the world's largest radiology website. And you can get a lot of images from here, and it's completely free. So this is a website what radiologists and radiology trainees use across the world. So it's a free, it's an open source, and it's a free data set you can download from here. It's a free resource. And so I visited this website and I downloaded some 100 data sets which were of the same patient. That is CT and MRI T1 images is what I downloaded. You will find a lot more variants, MRI T2 and MRI DWI and MRI flare. You will find quite a few images along with the MRI data set. But since I was working on CT and MRI T1, I just downloaded these images. And again, the image which was provided was of 16-bit int format. So I converted them to 8-bit int format in some cases, and some cases I continue to work with 16-bit int format. And on the website, you will also find a detailed case study about each of the tumors and how it was diagnosed and what was the outcome of the imaging, and how the expert radiologists have performed, the decision making, all the history of the patient, everything is going to be published on this website. So it's a good resource for people who are doing research in biomedical imaging. Yeah. now let's move to the next slide. So next I performed some pre-processing techniques, and of course I used a lot of filters to do the pre-processing. To name a few, I used anisotropic diffusion filter, and then bilateral filter, Gaussian filter. And after using all those filters, I discovered, I came across this non-local means filter, which worked very well with MRI images. So MRI images are mostly infected by a noise which is called as a Raysian noise. So you can see some results here. I have used this non-local filter, non-local means filter for denoising CT images and MRI images. And I have also performed, denoising on these images by varying the sigma, that is, by varying the distribution of noise in terms of sigma, that is 0.001 up to 0.02. I have varied the sigma, and then I have denoise the images, and you can see the results are all indicated here. Similarly, I performed denoising for MRI T1 images also with different sigma values. So the results are all here. So I think we can skip this non-local means filter. Yeah. And then I moved on to some contrast enhancement technique. So the adaptive histogram equalization technique is a very, very popular technique which is used to improve the contrast in images. And of course, if we are using the adaptive histogram equalization technique, there are quite a few parameters which have to be chosen. And some of the parameters I have listed here, it is clip limit, block size, the distribution function, and some of these, and there's something called as a window size. And there are some more parameters which have to be selected either manually or automatically. And there is no standard that, once you set these values, the same values can be used for all images. These values keep changing based on the nature of the images you're operating with. So there is no standard as such. So that was the challenge with contrast with the contrast limited adaptive histogram equalization technique. So I came up with a genetic algorithm, that is particle swarm optimization. I used particle swarm optimization to select all these parameters automatically based on some performance parameter like standard deviation. So we can just move to the next slide. Yeah, so these were some of the images I worked on. So you have the original image where the contrast is not very great. And then I performed, equalization techniques, the different equalization techniques. Again, it did not give very good results. As you can see, there is a lot of blurring, and there is some kind of shadow effect and all that. Whereas when I combined the Clahe and the particle swarm optimization, the contrast enhancement was much better. Again, the contrast enhancement I measured in terms of standard deviation, peak signal to noise ratio, and the structural similarity index. Based on these three parameters, I concluded that Clahe with PSO has given me good results. And this was a paper what I published based on the contrast enhancement technique. So this was published in IIITM Trivandrum in 2019. So next we'll move to image registration part. So this is the most interesting part of my PhD work. And of course, I use some AI technique here. So image registration is a very important and a mandatory requirement for registering the images before we perform image fusion. And usually the traditional image registration requires the following steps. That is, you have feature extraction, and then you have feature matching, and then you have model estimation and image transform. These are the steps involved in image registration, and they mathematically very, very robust, as in, each of them require a lot of mathematical algorithms to perform these operations. And of course, the applications are very clear. If we have a good registration technique, we can achieve early detection and precise estimation of the tumor can be made very easily if we have registered the images. So we'll move to the next slide. Yeah, so these are some of the challenges with the existing image registration technique. That is, it requires a ground truth image, which is also called as a fixed image, and or it's also called as a reference image. So every image you will be registering should be compared with a ground truth image or a reference image. And it's basically a iterative optimization algorithm, the traditional registration technique, and it requires a lot of execution time, and some similarity measures have to be identified, so that when I perform the registration, I can have these similarity measures evaluated, and then I know the images are registered. So again, there is a challenge here because iterative optimization algorithm. So because of these challenges, I moved to AI technique. That is, I designed a classifier which could identify the different classes of image positions or orientation or scaling, translation. I had designed a classifier which was capable of, identifying these classes. And of course, the challenge with designing the classifier was also not less, because when you design a AI classifier, you have to decide on the number of hidden layers, the hyperparameters like the optimizer, learning rate, epochs. All these things have to be, designed for. So this was the proposed CNN architecture, what I used, and of course I started with a very basic CNN architecture, just having 3 hidden layers. That is an input layer, output layer, and just 3 hidden layers. But of course, this with 3 hidden layers, we can't extract a lot of features, and that is when I started increasing the number of layers. So you can see there is, I think, 1, 2, and 3, 4, almost 4 sets of convolution layers. And along with the convolution layers, you have the clipped ReLU. So again, the ReLU or clipped ReLU, and you have many more, the ReLU layers which have to be chosen. So even that was taken care. Right, so this was the architecture what I proposed. And coming to the classifier, so the classifier would have 3 stages. The first stage is called as the angle classifier. That is, I designed the classifier which could detect different angles, so as precise as 2 degrees to 20 degrees. That is, 0 to 20 degrees is what we detected with the classifier. And it had 18 layers: the input layer, fully connected layer, softmax layer, and the last one is the classification layer. And these were all the layers which were designed. And then the training parameters also had to be chosen, like the optimizer, the steepest gradient descent algorithm, RMS prop, and the most popular is ADAM, that is adaptive movement estimation. And then the learning rate, epochs, all these parameters had to be designed or chosen. So after the first stage, after the angle is detected by the classifier, we move to the next stage, which is called as the angle correction phase. So depending on what class was identified, the image is going to be corrected for that angle. And then we perform the alignment phase. So when we perform alignment phase, we compute what is called as mutual information, or MI. This is the most popular similarity metric, which is used for checking whether the images are registered with each other or not. So this was done in the last stage. And this is how I used CNN to do the image registration. And you can see the various activation functions what I used. I use ReLU, leaky ReLU, and the clipped ReLU. And this was the accuracy what I achieved. It was 80%, 79%, and 95.4% with clipped ReLU. And of course, the execution time would also increase drastically. So from 9.42 minutes, it went on to 14.22 minutes. And all this was executed on the GPU. If I execute the same on the regular computer, it would take much longer time. The GPU would operate much faster. And then, of course, I tried with different optimizers also. So steepest gradient descent, RMS, and ADAM. I calculated the accuracy and the mini batch loss, the validation accuracy, validation loss. All these parameters were also computed. So these results actually help me decide what hyperparameter I have to choose for the classifier. And you can see some sample images here. You have a sample CT image, which is slightly disoriented. And after I perform image registration, this is how the CT image is going to appear. Similarly, the MRI image, you can see it is slightly disoriented, but after I perform image registration, it is going to be oriented correctly. And then I performed image registration the last figure what you see is where the image registration is performed. So you have images, which are not oriented in the same axis, but after you do the registration and then you overlap both the images one on one, and this is how the image is going to look like, right? When you perform image registration. So the mutual information was computed from this image. So the higher mutual information I get, it simply means that our registration has been successful. Right, so this was the image registration, what was performed, and this is some of the graphs for the accuracy and loss. And these were the various classes what I identified. So from 0 degrees to 20 degrees, and each class differing with 2 degrees, right? So I created the data set where I performed augmentation, and each of the images were tilted by 2 degrees each. So from 0 degrees, 2 degrees, 4 degrees, it went on up to 20 degrees. So this is how we have these 10 classes. And after we performed the classification, this is the confusion matrix which is being shown here. And apologies for the resolution of the images because I copied from the slides. I think the resolution is not very great. But I will give you the source for the papers which I have published on these results. So you can always refer to these papers for the results. And you can see here, I have done the registration and fusion also. So in case we don't perform image registration, so if we have a CT image like this one and an MRI image which is slightly disoriented, and if I don't perform image registration, I just go ahead and fuse the images or register the images. This is how it is going to appear. I have used different colors to show that there are two different images in the registered image, right? So here you have another case where you have a CT image and MRI image of different scaling. So again, if the scaling is not uniform, you perform registration and fusion. This is how the image is going to look like. And if I ensure the scaling and the orientation is all equal, and then I perform registration, this is how the image is going to appear. So I had some performance metrics here again for minimum square error, PSNR, and SSIM. So with registration, we can clearly see there is an improvement in MSE, PSNR, and SSIM. So performance metrics are very important to evaluate the efficiency of the algorithms. And these are some of the papers I published based on the classifier what we designed. So the first was a conference paper which was published in 2020. And the second one is also a conference paper which was published in IIT Guwahati in 21. And next we'll move to the image fusion techniques. So in the image fusion techniques, I use the discrete wavelet transforms and the Laplacian pyramid and non-subsampled counterlaid transforms. Again, these are going to end up giving a lot of redundant information which can be avoided by sparse representation. So I performed fusion with each of these transforms and a combination of sparse representation. So this achieved good results. And you can see some of the results here, like the CT image. I have a CT image with some standard deviation and SSMI indicated. And in case I segment the tumor from a CT image, this is how it is going to appear. And the number of pixels, the area is going to represent the number of pixels which were segmented from the image. I did a similar exercise for a MRI T1 image. Again, the number of pixels is 509 here, which is segmented. And then the Laplacian pyramid with the sparse representation gave very good results in terms of standard deviation and structural index similarity. So you can see when I performed the image fusion, I performed registration and then image fusion and then segmented the image. And you can see the area here, it is 1413 pixels. Now the same image I handed over to a doctor, to a radiologist to manually segment the tumor and then identify the area. So the doctor was able to identify 1431.89 pixels from the DICOM software. And so this is kindly slightly approximate figure, right? 1431, and through our proposed technique we have 1413, so it's almost close. In fact, it is more precise here with the proposed technique, right? And even if you look at the MRI image, when the doctor segments the tumor from the MRI image, he ends up identifying more number of pixels, whereas with the proposed technique, it is more accurate. Yeah, so the CT also, you can see there is some difference here with respect to the manual segmentation and the segmentation performed through the proposed technique. Right? And these were some of my papers, the outcome of the image fusion. So I managed to publish some of the papers in journals and some in conferences. Yeah, so now we will move to AI tools for research. If there are any questions, I can take it up. Any questions so far?
Dear participants, if you have any questions, please.
Madam, how you have collected the this one images?
Sorry, ma'am. Can you please?
Images you said no one website. Which website?
The Radiopedia. It is radiopedia.org.
From that, if you give image name, that will come.
Yes, ma'am. It's an open source website. You can download a lot of images. It's not only for the brain. You get imaging information of all the body parts. Even if you are looking for some lung images or breast images, you get a lot. It's the world's largest radiologist website, radiology resource. So a lot of doctors upload this information on this website. A lot of doctors will upload information. So it is an authorized resource. Otherwise, if you approach the hospitals, a lot of hospitals don't share the data because of privacy and the patient information. It's very secure. So a lot of hospitals don't share the information. But these resources you can always use for free without any reservations. It's radiopedia.org. I have mentioned in the slide. You can visit the website. Any other questions? So all these images, whatever I have used, it's all coming from radiopedia.org. Any other questions? Can we move to the next slide?
Okay, ma'am.
Yeah, thank you. So next, I would like to touch on some AI tools for research. So these tools, somewhere towards the later phase of my PhD, I was aware of all these tools. But now I think we have a lot of AI tools which can do our research much faster. So coming to some AI tools, what I have used myself. So to do literature survey or literature review, there's a very popular AI tool which is called as Lit Maps. I have indicated it here, Lit Maps. So if you just put the title of the paper, it is going to show you the entire, the history of the paper and who has used the paper and, how it has been navigated, how the authors have written the paper, based on which papers they have referred and they have written. And after that paper got published, who are the other people who have used this paper, right, who have referred this paper. So Lit Maps is a very, very useful literature review AI tool. So please take a look at it in case you're doing some literature survey. And of course you have Undermined and you have Insightful also, but these come with some some kind of payments, but Lit Maps is completely free, so you can use Lit Maps. And then you have some AI tools for data extraction. It is SciSpace, Perplexity I have used, but again it's a paid version, so you can try that. And then when you're writing the paper, there are quite a few tools. I think Grammarly and Quillbot is widely used, but otherwise you have some more, writing tools like PaperPal and Trinka and Writeful. So these come with some kind of payments. So some basic plan you will have to buy if you have to use these tools. But otherwise, Quillbot and I think Grammarly is completely free. The free version is you can use it. But again, if you're looking at for more features, even they have the paid versions. And then you have some AI tools for data analysis. So once we have the results, when we generate the graphs and we are trying to make some conclusions from the graphs, right, that is also pretty challenging. So these AI tools come handy. So you have Tableau, you have Julius, and you have Insight 7. These are some of the data analysis tools. So you just feed your data, you put the results what you have got, and these tools will help you generate beautiful graphs and all the bar graphs or the line graphs can be easily generated. But of course you have to tweak a little to make it more similar to what you are looking for. And then of course you have the reference management. So when you're doing research or when you're doing PhD, I'm sure we refer a lot of papers, and most of the time we forget which paper we used more, or which is very important, and so on. So some reference management tools like Paperpile and Thryrix and Petal, these are some reference management tools you can use. And you have data visualization. This is also used to generate some graphs or some block diagrams. If you want to make, you can use this. And there's another tool which is called as Draw AI. Draw.ai is what you can use if you want to make some beautiful block diagrams. And of course, if you want to get your paper reviewed by your peers, you can easily share it through Review It or Enago or Penelope. These are, you can share it easily with anybody using these AI tools, and you can get your papers reviewed. So that's about the AI tools. So I will share these slides. I think you can visit these websites and take a look at them. And this is the call for doctoral fellowship, which was made by RNSIT, and this is a rolling application. It is open throughout the year. In case somebody wishes to pursue their PhD, they can always sign up for the doctoral fellowship, where you can work in RNSIT as a research fellow. And there is going to be a stipend of 25,000, which is going to be paid to each of the research scholars. So you can do a research, and you can also get a stipend here. So in case anybody is interested, you can connect with me sometime and we can discuss about it. And now coming to some of the open problems with image processing and AI. So these are some of the open problems you can think of working on. You have generative AI for image synthesis, like the gangs, where you can generate, if you just put the text, it is going to generate images for you. So the application is listed here. It is used for deep fake detection or AI generated art. I think we are seeing a lot of these things, in social media now. And then if you want to generate some synthetic data for training or machine learning models, they can be generated using gangs, which is called as generative adversarial networks. And then you have super resolution or image enhancement techniques, where we use deep learning based techniques to increase the resolution of images. So in case you have low resolution cameras, the images coming from them are not very of high quality. So you can increase the resolution by using some deep learning based resolution techniques. So it can be used in medical imaging, satellite imagery, or security applications. And the very popular one now is called as Edge AI or Tiny ML models. So there is always a demand for lightweight AI models. We all know AI models, they come with their own drawbacks, like they are data intensive and a lot of computations are involved. So there is always a challenge to design lightweight AI models which can be easily deployed in edge devices like your mobile phones or drones or some kind of IoT devices. So this is also an emerging field in image processing with AI. And then of course you have self supervised learning for image understanding. So most of the data sets, they are labeled, but however you can also have cases where you have unlabeled data. So if you have unlabeled data, then how will we train the neural networks, or how will we train the classifiers? So there are ways to handle such things, so which is called as self-supervised learning for image understanding. So some techniques like SimClare or Muko or Biol, these are some of the techniques which can be used for unsupervised, or self-supervised learning or unlabeled data if you have. So it helps in medical imaging or industrial defect detection, where labeled data sets are very scarce. There are cases where you don't have labeled data sets, right? There is no annotation for the data. In that case, we can use any of these models. And you have neural radiance fields, that is generating 3D images from 2D images. So that is called as neural radiance fields. So this is widely used in virtual reality, augmented reality, or some gaming, gaming softwares, or if you want to make a digital twin, that is where this kind of, approach is adopted. And the next one, you have explainable AI, where you use AI models to interpret, the trustworthy, techniques like GradCam or Sharp to explain their decision making in image classification. See, most of the times what happens is whenever you design the neural networks, it is going to give you the right result, and it is going to purely depend on the training, right? How much data you have and how well you have trained. The result or the accuracy is purely going to depend on the training, right? But if you don't have enough data, then you fail to have a very good classifier, to build a very good classifier. And again, how this classifier is operating, how these neural networks are operating, that is all about explainable AI. So explainable AI deals with how all of these neural networks are operating, right? So it's a very essential field again in all the imaging applications. And of course, we have AI in medical imaging. So there are a lot of AI techniques being proposed in medical imaging. So the latest one, it is called as DeepMind's AlphaFold, which is revolutionizing the protein structure prediction from imaging data. So from the imaging data, it's able to predict the protein structure. So this is a very revolution AI assisted tool. And of course, since I'm very closely associated with IEEE, some of the IEEE journals you can refer for doing your research is going to be IEEE transactions on image processing, IEEE transactions on artificial intelligence, on pattern analysis and machine intelligence, and you have IEEE intelligent systems. So these are some of the very renowned journals which you can refer, and you can get a lot of information from these journals. And of course, coming to the IEEE societies, you have IEEE Signal Processing Society, IEEE Engineering, Medicine and Biology Society, and Women in Engineering Society. So I closely work with these three societies. I am also serving as a ExeCom member for the Bangalore section on these three societies. So these forums help us to learn and understand the latest techniques, and also network with a lot of experts, get access to a lot of new resources. So I think it's very important that all of us have a IEEE membership and collaborate with these societies. And some of the flagship conferences you can look forward to is ICASP, which is International Conference on Acoustics, Speech and Signal Processing. So this is happening in Hyderabad in April 6 to I think 11, 2025 this year. And this is the first time this conference has come to India. It has never happened to India, and it's a flagship conference by IEEE SPS. So in case you get a chance to attend this conference, it would be wonderful. The registration is still open. And you have another conference, which is International Conference on Image Processing. And you have International Symposium of Biomedical Imaging. So these are very, very popular conferences. And if you look at the papers coming from these conferences, they are highly cited, and some very good and novel techniques are being discussed in these papers. So this is my Google Scholar link and my LinkedIn link. If you wish to connect with me, you can do it on these two links. You can go through the papers which are indicated here in the Google Scholar. And of course, I'm very active on LinkedIn as well. So you can connect with me in case you're looking for some collaborations or some kind of assistance for project or internship or placements or anything as such. So I would like to conclude here with a thank you note. And if there are any questions, I can take it up. So I would not like to bombard a lot of information because it being the afternoon. So I will keep it short and simple, but yes, of course, we can always connect, offline and have a discussion if anybody is interested. So if there are any questions, I can take it up.
Participants, if you have any questions, please. So madam has given a vast information regarding how to get the data sets. So the collection of data is very, very important for any research. So how easily you can get the data. So that information it is shared with madam. It's very useful. And
Yes.
so many of the as a researchers, so many of the researchers are facing some difficulty in the collection of the data only. So
True, sir. True.
from your side, we got that information. So
Exactly. And I think the AI tools also, if you start using them more, it makes your life very easy.
yeah,
The researcher, AI tools come very handy.
yeah.
Yes.
Dear participants, any questions? So madam has given the contact details. So if you have any assistance, you can contact ma'am.
Yes.
Dr. Siddesh, HOD, Department of E&CE, will thank the man.
Good afternoon, madam.
Good afternoon, sir.
You have given a wonderful input to our participants on image processing, data sets, research on this, and a lot of how to use the journals, AI tools. So a lot of
Yes.
participants has given by you, sir. And I hope all the participants will utilize this knowledge and keep in touch with the in future, madam. Please.
Sure, sir.
Yeah, please. Thank you.
Yeah, thank you, sir. Thank you so much. I have kept it very short because it being the afternoon, a lot of theory will not, people may not like it at this time of the day. So I've kept it very short, but I'm always open for discussions. People can reach out to me. That's not an issue at all.
Okay. The feedback will be shared in 1 minute and it will be open for 15 minutes. Please give the feedback within the prescribed time. Thank you, ma'am.
Yeah, thank you, sir. Thank you so much. I will stop sharing the screen.
Yeah, okay. Tomorrow morning, there will be a session by Venkatesh sir, Brilio Technologies, Bangalore. He is a senior lead quality engineer. Okay, tomorrow at 10 o'clock, he will be giving the lecture. Thank you.
Campus thing,